Yes, sir. I can record now.
Going into the VLSI thing, let's start with a previously known topic, that is NMOS or PMOS, right? MOSFET. How MOSFET works. I'm going to teach you how an NMOS works, and PMOS, how PMOS work, you can guess from itself. And at first, how NMOS is made. NMOS is made by using PMOS, but by using P-type material. This is a P-type material, P-doped silicon, right? P-doped means what? When the silicon is there, that is okay, and it is useless at the very first time because it do not have any free electron. Got my point? So what people does, people actually use some doping material inside that, so that what happens, it gets some free electrons. So I will be giving you a video for this reference. You can see that video. And what is N type? N type is when you mix, silicon has 4 electrons. Silicon has 4 electrons at its outside, okay? 4 electrons. So what happens? Silicon creates covalent bonds with its neighboring what? Neighboring silicon. Got my point? It creates covalent bond with its neighboring what? Neighboring silicons. So as you can see, so it will form another bond. So it will form another bond. It will form another bond. So every silicon will create covalent bond with another silicon atom. So that time it will not have any free spaces. You can see here how many electron does how many electron this silicon has. 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons. That means it do not have any free electrons. So it cannot conduct any current. So it is useless. It is non-conductive. So what people does, people mix some impurities here. That is called doping. People mix some impurities here. Normally, maybe arsenic, maybe boron, something like that. For N type, when you mix something, for N type, if you mix something for N type, what happens? It has 5 electrons. Silicon has 4 electrons, it has 5 electrons. So among those 5, 4 of them will create covalent bond and 1 will become extra. So these 4 will create bond with the neighboring silicons, and this 1 will become extra. This extra then moves. That means electron is moving through the silicon. That time it can conduct current. This is called N-type material. Now what is called P-type material? When you mix something here, P-type has 3 outside electrons, 3. So what happens? 3 of them will create bond with neighboring silicon. So you have one space left. Space. Do you understand space? You have one space left. That space is called hole. H-O-L-E, hole. That means 1 electron can come and sit here. This electron can come and sit here. Got my point? In that case, this will be the empty now. Another electron will come and sit here. That will be the empty now. So electrons are moving. This is how electrons are moving. I will give you an animation video for this one. So always remember, p-type materials means you have holes. That means you have scarcity of electron. You have some places there electron can sit. Okay, but that doesn't mean that it do not have any free electron. It has some free electron, but it will be very less. So we will take a p-type material first that has some hole inside. So it is p-doped silicon. Then on that p-doped silicon, we will create some drain and source, like these. We will create some drain and source. This pink color thing, this is an n-type material. That means on top of p-type, we will create n-type. So these red colors, those are electrons. So those green colors, those are holes. Okay. So these are electrons. Okay, extra electrons. So n-type. This is n-type. This is n-type. Next, we will create a silicon dioxide layer on top of the that small space. That is small space. We will create and what? A layer of silicon dioxide. Silicon dioxide. This one is silicon dioxide. This one is an insulation. Remember, on top of the silicon dioxide, we will create a layer of metal. This is the metal. This is our gate. Then we will cover that with a casing. You know, casing, a cap. We will cover that with a cap. Then you can see there are 3 holes there. 3 holes. 1 hole, 2nd hole, 3rd hole. This hole is connected to this one. This hole is connected to this one, and this hole is connected to the gate. Okay, these are your pins. These are your 3 pins for your what is that called? Transistors. Okay, so let's give some pins here. These are 3 pins. 1, 2, 3. 3 pins. Now let's see how this thing works. Let's call this is our source. This is drain, and the middle one is our gate. So this is p-type. This is called bulk, body, or substrate. Bulk, body, or substrate. This is n plus. This is n plus. This is p. Now in the n plus, you have lots of electron, lots of free electron. In the metal, you have lots of free electron, lots of free electron in the metal. Okay, but in the p-type, you do not have enough electron. You have holes. Okay, but you have not enough electron. So what happens when you apply a battery here? So electron tries to come. Electron try to come from here. Try to complete the loop. Okay, electron try to come from here and complete the loop. That means it want to create a current flow, but this part is metal. It has electrons, so electron can move inside. This part is metal. It has free electron, so electron can move inside. This pin is metal, so it has free electrons, so it can move. This pin is metal, so electron can move. Here this is n plus, so they have free electrons, so electron can move. Here electrons, free electrons, so electron can move. But in this part, that is here, you do not have any what? You do not have any free electron, or you have but very less. So what happens? Their electron cannot move, so current will not flow. So there will be no current. So how can you create some current here? You have to create a bridge. You have to create a bridge so that the electron go. So how to create that bridge? You will bring a magnet. You will bring a magnet in the gate. So what happens? Right now you have, okay, let me clear. You have holes. Right now you have a lot of holes here, okay, in the whole segment. All are holes, and you have very few free electron. Very few free electron. Got my point? Because it is p-type, you have a lots of holes, but very few free electron. Okay, so once you bring one magnet here, magnet means what? What attracts electron? Positive voltage attracts electron. Negative voltage attracts hole. Okay, positive voltage attracts electron and repels hole. মানে পজিটিভ ভোল্টেজটা হচ্ছে ইলেকট্রনকে আকর্ষণ করবে আর হোলকে বিকর্ষণ করবে। So positive voltage will attract the electron and repels the hole. So what you can do, you can bring a positive voltage here, once you bring a positive voltage here, what will happen? All the green dot will go lower. Okay, because they are repelling, and all the red color, not all, some, this red color will go up. Because this positive voltage is attracting all the electrons there. So all the, or some of the, or most of the electron will go there. Got my point? What happened? Understood, everyone? When you apply positive voltage here, all the green dots are going away, all the red dots are going up. So now you have a bridge. Can you see you have a bridge here? Can you see that?
Yes, sir.
So you have a bridge. So once you have a bridge, now electron can go. So তখন current flow করবে. If you want to increase the flow of the current, you have to make a bigger bridge. That's my point. You have to make a bigger bridge. That time you will bring a bigger magnet. What this magnet will do? This magnet will repel these green color things further. এগুলা আরো দূরে সরাই দিবে, and it will attract these remaining reds. বাকি যে রেড গুলো ছিল এগুলোকে সে কাছে নিয়ে আসবে। Got my point? Now you have a bigger bridge. Now more current can go. So your current is increased. Okay. Now you can see you have a bridge. So these green color plus things will repel the hole and attracts the electron. Now electron can move. You can see electrons are moving. If you want to increase the current, you need a bigger magnet. That means bigger voltage. That you have to increase the gate voltage. This is called gate voltage. This voltage is called gate voltage. That is VG. Okay. You have to increase or VGS because your source found it. So when you apply a voltage, it is always measured from the source. তুমি যখন একটা ভোল্টেজকে এখানে অ্যাপ্লাই করবা, সেই ভোল্টেজটা সব সময় গ্রাউন্ডের সাপেক্ষে কি করা হবে? মেজার করা হবে। সো যেহেতু আমাদের গ্রাউন্ডটা হচ্ছে আমাদের সোর্স, এই জন্য এটাকে ভিজি না বলে এটাকে ভিজিএস বলা হয়। সো উইল look into that later. No problem, do not worry. So when you apply more gate voltage, what happens? It will repel the hole further, and adds more electron. So now more electron can move. You can see previously there are less electron. Now you have more electrons that are going. That means your current increased. Okay. So this was the this was the basic of your NMOS. So I can give you some insight. I can give you some what is that animation video from YouTube. You can see. Let me show you how transistor works. Okay, here you have one good video of this one. How it's created. So I'm going to give it to you. So you can just write how transistor works or how do they work. This one. Okay. This is the main video. You can see. No, not this one. This is the main video. You can see it by yourself. Here you have a concept of silicon bonding and doping. But my point, you watch this video carefully. Let's go to our lecture. Our first computer. Because we are living in an era, we have computers and we are using it every day. Unlike some of you do not use computers. Some of you just write your assignment using hand. Okay. But most of us use computers because we have computers. This is an era of computer. And the first computer was created or built in 1832. That was not practically a computer. That was a difference engine. That was a difference machine by which you can subtract numbers. Okay, by which you can subtract numbers. So who created that? Charles Babbage. He is the founder or he is the inventor of computer. And this machine is called the Babbage difference engine. Babbage difference engine. Okay, Charles Babbage. And how this thing works? You can see you have 3 rows of numbers. This is one row. This is another row. This is another row. And you have some gears. Okay, and you have some numbers. As you can see here. I can say 3, 1, 1, 1, 1, 3. And here you can see 9, 9, 9, 3, 0, 9. Okay. So these are the numbers like this one. Okay, let me show you something. You have seen these, right? All of you have seen this. All of you have seen this technology, right? All of you have seen this tech, right? How this lock is open, do you know? Because there are some gears inside, there are some locking mechanism inside. Once you rotate this number, something rotated inside. Okay, something rotate inside. So what happens here? Once you rotate the number, the gears are rotating. Once you rotate this number, so gears are rotating. So here this is, let's say this is called A, let's say this is called B, and let's say this is called result. So when you rotate the A, that means these individual numbers, this gear will rotate. Once you rotate this number, the gear will rotate. So these 2 gears will create something and will automatically rotate this number. Okay? Got my point? So when you rotate A and B, that will rotate the result column and that will show you the result. So you will have a what? You will have a number here, that is your A. You have another number here, that will be B. So when you rotate them and fix the number, your result will be automatically matched, automatically rotate. So you can see this is your A, minus B equal to our result. So this was the Babbage computer by using mechanical part, no electronic, nothing. And in that time, it has 25,000 parts and it cost 17,470 pounds in that time. Remember, this is huge money, huge money. During that time, this was huge. Okay. Okay. This was the first electronic computer. You can see the date. See the date. It was 1832. This one is 1946. After 120 years. This was called ENIAC. ENISC. ENIAC. Remember this name. Remember this name throughout your life. ENIAC was the first electronic computer. Electronic, but not transistor based. No, there was no transistor here. No transistor. Do you know why? Because transistor was created in 1947. Transistor was created in 1947 and this was in 1946. So there was no transistor here. So this was the first ENIAC, first electronic computer. These are based on vacuum tube. This was based on vacuum tube. You can see the video I mentioned. It has the concept of vacuum tube there. You can see this was based on vacuum tube and some numbers, some switches. You can see some switches here. Switches, right? Some switches are there. You can see that. And some cables are there. So there are operators. Here you can see 1, 2, 3, 4, 5 persons, 4 persons are conducting the operation of the computer. The whole room is the computer, and the whole room is the ENIAC, first electronic computer. Okay. Now this is an ASIC. Remember this. ASIC is application specific circuit. Application specific integrated circuit. Do not forget this. Application specific integrated circuit with mixture of full custom design, RAM and standard cell. What is full custom? We will know. Do not worry, we will know what is called full custom. Okay. Now ASIC is application specific integrated circuit. This is a circuit that is made for a specific application. Let's say this is for TV. Let's say this IC is made for TV. TV, do you know TV? Television. So the application is specific. Application is specific. That's why this is called ASIC. And this is Pentium. Pentium is the Pentium 1. See, before Core i3, Core i7, there was dual core, quad core, Pentium 2, Pentium 3, Pentium 4, Pentium 1. Okay, Pentium 1 was maybe in 1990s. That means 1993 or 1994, something like that. Okay, Pentium 1, Pentium 2, Pentium 3, Pentium 4, Pentium D, dual core, quad core, core 2 duo. Then comes the Core i3 or Core i5 or Core i7. Okay. So this is a Pentium. So there you can see some designs. Okay. There you can see some designs. Can you see that? This is the Pentium design. Now let's see the Core i7 design. Or Core i9 design. Nope. This one maybe. This is mobile CPU, not Core i9. Yeah. Very small. Maybe this one is something like that. A new processor, core processor. Okay, you can see this part is called processor graphics. This is 1 core, 2 core, 3 core, 4 core. So this is a quad core CPU, quad core Core i3 or Core i7 or Core i9. I'm not sure. Quad core. That means you have 4 cores. Okay, 4 cores. And this is your system agent and memory controller. That is the RAM controller. RAM. So you give some data, you get some data. This is your share L3 cache. We'll learn about this later. This is called SRAM. SRAM, okay? Static random access memory. Static random access memory, SRAM. This is the RAM, but it is also called L3 cache memory. Okay, so this is, you can see some colorful design. These are called mask layout or architecture, whatever you say, layout or architecture. This was the mask layout of Pentium. Now, before going into the moods though, see something else. Okay, this guy is called Julius Eaglefield. He was an Austro-Hungarian or Austro-Hungarian physicist. Austro-Hungarian physicist. That means he actually lived in Austria and Hungary and somewhere else. And now it is called Ukraine. That place is now in Ukraine because of the border issue or political issue. And he moved to United States in early 1920. In order to defend patents he possesses, he went to United States to defend his patents. Then scientific or industrial career there. He invented a FET-like transistor and an electrolytic capacitor in 1920. He invented a FET transistor C. He invented, that means he invented something that is a FET-like transistor. There is a FET-like transistor. FET-like means FET, field effect transistor, like transistor. Okay, got my point? Remember, he invented, not created, because he actually invented on paper, theoretically, a transistor, a FET-like transistor, and electrolytic capacitor in 1920. So that was the beginning of the transistors. Okay, now when he created that in 1920, that was accepted in 1930. Accepted. Do you know what accepted means? Accepted means after 10 years it was accepted. Okay, then he received a major prize for that. Okay, brief history. FET-like transistor by Julius Eaglefield was created in 1920. First transistor was created based on that FET-like transistor in 1947. Three scientists created that: William Shockley, John Burdine, and Walter Brattain. They created a germanium transistor. Germanium, remember, germanium, not silicon, germanium. Okay, they created that, and for that, all three of them get Nobel Prize. They created the transistor, and for that, all three of them got Nobel Prize, because of their invention, we are here now. We have everything now. We have Facebook, we have computer, we have camera, we have a mobile phone, we have health equipment, we have rocket, we have everything because of them. Okay, got my point? In past 80 years, we have seen tremendous amount of scientific achievement because of this thing, because of the transistor. First was created fire, right? Then what? Then wheel. Then what? Then what? Can anyone explain? Then what after electricity? Now we have internet. These are the 5 things that change the history of the mankind: fire, wheel, electricity, transistor, and then we have internet. So transistor is a big thing. That's why all 3 of them got Nobel Prize. 1947, and this was germanium, but not single crystal. All of them were separated. Now then, 1950, they created single crystal germanium, not multiple crystal. This was multiple crystal, then you have the single crystal. Then 1952, they were able to create single crystal silicon. So silicon comes later. First IC device was created by Jack Kilby in 1958 by Texas Instruments. Then first IC product was for a camera, Fairchild camera, the chip for a camera. It was created in 1961 by Robert Noyce. Okay, so let's see some pictures. This was the first transistors that was created in Bell Lab. Bell Lab is a very famous lab because of the transistors was created there. That's why it is a very famous lab. Bell Lab, the first transistor was created in 1947. As you can see, there are multiple crystals. 1 crystal, 2 crystal, 3 crystal, something, multiple crystals were there. These 3 guys, the middle one was William Shockley, John Bardeen, and Walter Brattain. They created the transistors. This was the first IC device, IC. So here you can see 4 pins, 1, 2, 3, 4. 4 pins are there. This is the first IC device. Was created by Jack Kilby, Texas Instruments. This was the first chip, first commercial chip that was created in 1961 for Fairchild camera by Robert Noyce. Okay, as you can see, the first transistor was huge. This was big. After some moment, you can see the transistor becoming smaller. This one is smaller. Here, this one is very small. This one is very small. Okay, so you can see the transistor was becoming smaller, smaller, smaller. The transistor was becoming smaller. In 2000, the transistor size was this. In 2015, the transistor size is this. So transistors are becoming smaller. Got my point? So from this trend, a guy called Gordon Moore gave a law. Actually, he gave a law. Gordon Moore, he gave a law. Who is Gordon Moore? Gordon Moore was the co-founder, Intel co-founder and chairman of Emeritus. Okay, Intel. Do you know Intel? Intel Core i3, Core i7. He was the co-founder of Intel. In 1965, Gordon Moore predicted. মানে উনি ধারণা করছিলেন. He predicted that the transistors would continue to shrink. That means what? Transistor would continue to shrink. Transistor কিন্তু ধীরে ধীরে ছোট হবে. Transistor will continue to shrink. Transistor would continue to shrink, allowing double transistor density in every 18 to 24 months, double performance in every 18 to 24 months. Double transistor density means in single space, in let's say, okay, this is 1 centimeter square. This 1 centimeter square, if we have 1000 transistors today, after 18 to 24 months, that means 2 years, after 2 years there will be 2000 transistors, that means double density in the single space, that means in the same space we will have double transistors, that is called double transistor density. And since the transistor become double, so the performance will become double. That is, in every 2 years our mobile phone is becoming powerful. Okay, before 2 years what was the phone? After 2 years what is the phone? You can see the performance is double, because you have more transistor now, you have more people to work. Okay, so what is the law? In 1965, Gordon Moore predicted that transistor would continue to shrink, allowing double transistor density in 18 to 24 months, double performance in 18 to 24 months. And the history has proven Moore right. So far, he is right. So far, he predicted this in 1965, and so far he is correct. But will he be correct forever? Will he be correct forever? Or it is going to end very soon? Is the end is in sight? That means, is this going to be failed? It is going to be failed very soon. Why? Because of the physical limitation, because the economic limitation. What is called physical limitation? So previously this was the size of the transistor. These are size of the transistor become this one. Okay, after 2 years the size of the transistor will be this one. After 2 years the size of the transistor is this one. Got my point, everyone? Hello?
Yes.
Okay.
Yes, sir.
A time will come when your electron will be bigger than your transistor. Got my point? Your electron will be bigger than your transistor. That time you will no longer be able to create transistors. Okay, because remember I told you at the beginning of the class, we are going to make a bridge, right? We are going to make a bridge. But what happens? You do not need a bridge. What happens? You can jump. Got my point? Let's say you have a river in front of you. তোমার সামনে একটা নদী আছে. To cross it, you need a river, you need a bridge, right? Hello? Cross it, তোমাকে একটা cross করতে হলে bridge লাগবে. What happens if the river is so small, you do not need a bridge, you can just jump, right?
Yes, sir.
You need a bridge now? Do you need a bridge?
No, sir.
If you can jump, you do not need a bridge. That means you do not need a transistor. That time there is no need for a transistor. That is called physical limitation. So by becoming smaller, once you will see, you cannot make this any more smaller. Okay. Now what is economic limitation? Let's say you can make the transistor smaller. Some chances, there are some capabilities, there are some machines by which you can make the transistor smaller. But if you want to do that, the cost become higher. The cost, the price, the cost become higher. Then will people buy it? People will not buy it. So there is no need of doing that. So that is called economic limitation. So either way, physical limitation or economic limitation, this will stop someday. Okay. So okay, whatever. At the beginning, the rate was 12 months. It slowed down. 1980s, it became 18 months. Nowadays, it is 24 months. Okay. So these doubling the transistor, doubling the what is that performance, it was 12 months. The gap was 12 months. 1980s, the gap becomes 18 months. Nowadays, it becomes 24 months. So that is it. From this this class, we will start our main teaching or main